Hi, welcome to All About Mechanical Engineering. In the previous video, we have discussed the polytropic process and we have seen how we can use this relationship, and by changing the value of n, we can obtain the various processes. Now in today's video, our work is to find the value of work done during the process, that is polytropic process, and the amount of heat supplied or rejected during this process. Here in the previous videos we have studied adiabatic process, which has a similar equation as written here. For an adiabatic process, we have PV raised to gamma equals to C. Now if you carefully observe these two equations, the only difference is the power, that is index. Here it is n, here it is gamma. In our previous video, for an adiabatic process, we have calculated the value of W, which was given by P1V1 minus P2V2 divided by gamma minus 1, which can also be written as R into bracket T1 minus T2 divided by gamma minus 1. Using the same derivation, same steps, if you replace gamma by n, then we can find out the value of W for a polytropic process, which will be obtained as P1V1 minus P2V2 divided by n minus 1, which is also written as R into bracket T1 minus T2 divided by n minus 1. So this is the amount of work done for a polytropic process. Now the question is, for an adiabatic process, Q is directly 0. Now we are required to find the value of Q for a polytropic process. As per our first law of thermodynamics, for any system undergoing a process, Q is equals to change in internal energy plus work done. For a polytropic process, W can be written as this, and delta U is nothing but change in internal energy, and that is nothing but delta U is equals to mCV T2 minus T1. Writing this for a unit mass, m becomes 1. So here I can write it as CV into bracket T2 minus T1 plus, substituting the W from this, R T1 minus T2 divided by n minus 1. Now I have not used this formula because here I need something common, and here T2 minus T1 is a bracket which is coming common. Writing this bracket in terms of this, by rearranging we can write R into bracket T1 minus T2 divided by n minus 1 minus CV into bracket T1 minus T2. Now I have T1 minus T2 as common. I need something more as common. From our relation CV equals to R divided by gamma minus 1, if I put this value here in this, then we get something else as common. Let us put this value. Q is equals to R into bracket T1 minus T2 divided by n minus 1 minus R divided by gamma minus 1. In bracket we have T1 minus T2. So here R into bracket T1 minus T2 can be taken as common. So taking it out as common, R divided by R into bracket T1 minus T2. Here in bracket it remains 1 divided by n minus 1 minus 1 divided by gamma minus 1. Cross multiplying this bracket, we can have R into bracket T1 minus T2. Here gamma minus 1 in one bracket minus n minus 1 divided by n minus 1 in one bracket and gamma minus 1 in another bracket. Now multiplying by minus 1 and opening the bracket, simplifying it, we get R into bracket T1 minus T2 into bracket gamma minus 1 minus n plus 1 divided by n minus 1 and gamma minus 1. Here minus 1 plus 1 gets cancelled. Here we have gamma minus n divided by here gamma minus 1. Then we have r into bracket T1 minus T2 divided by n minus 1. So this term is nothing but our W. So here Q is nothing but gamma minus n divided by gamma minus 1 into W. So this is the amount of heat supplied during a polytropic process. So we have calculated W, we have Q. So this was all about a polytropic process. I hope you have enjoyed this video. Please like and subscribe our channel and stay connected with us. Thank you.